Hello, my name is Courtney Payne, Associate Editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the High Performing Buildings Supplier Webinar Series. The series provides information of interest to HPB readers and others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. The following presentation has been prepared by Mitsubishi Electric Trane HVAC US on the subject Applying VRF Systems in Cold Climate Applications. Today's speakers from Mitsubishi Electric are James DeBerry, Commercial Marketing Manager, and Mike Machemehl, Senior Manager, Commercial Channel Strategy. James develops and executes marketing plans for Mitsubishi Electric's commercial new product launches and existing product maintenance. With extensive corporate marketing experience, James most recently served as Senior Marketing Manager at AT&T Atlanta. He is a graduate of the University of Georgia with a degree in journalism. As the Senior Manager of the HVAC Commercial Channel for Mitsubishi Electric, Mike is part of the team that creates sales, marketing, and channel development plans for the commercial markets in the United States for the City Multi-Commercial VRF product line. A graduate of The Ohio State University, Mike is a registered professional engineer in the state of Ohio, a certified energy manager, a lead green associate, and has over 30 years of experience in the commercial HVAC market, including 19 years as a Trane account manager in the Columbus, Ohio market. Mike is also an accomplished speaker in the building industry, having presented to a multitude of professional organizations, including AIA, ASHRAE, and USGBC. James, the microphone is all yours.
All right, thank you very much, Courtney. Good morning or good afternoon, depending on where you're joining us from today. I'd like to welcome you to today's webinar entitled Applying VRF Systems in Cold Climate Applications. On behalf of Mike Machemehl, I'd like to thank you for the time you've chosen to invest in today's session, and both Mike and I believe you'll find the content presented to be quite valuable. We're planning to spend about the next hour discussing VRF, or Variable Refrigerant Flow technology, and explore some solutions for today's commercial marketplace and how they perform in cold climates. The learning objectives for today's webinar include: we'll start by describing how modern VRF systems perform in cold climates. We'll talk about designing systems to solve derating challenges and recognize when to apply flash injection technology and water source VRF systems. We'll also talk about designing and installing systems with precautions for snow and cold weather. And lastly, we'll discuss how applying VRF technology supports strategic electrification and decarbonization in cold climates. Mike and I look forward to sharing our thoughts on VRF technology and some of the characteristics and advantages it offers for cold climate applications. We'll also look at a couple of successful case studies, and we'll share some additional resources for continued learning at the end. We'll also have some time at the end of the presentation to address as many questions as possible, so be sure to submit your questions throughout the webinar using the Q&A function within the presentation interface. With that, let's get started. I'd like to start by talking a little bit about what are VRF systems. VRF systems heat and cool zones by moving conditioned refrigerant through small diameter piping. VRF systems are electric powered and do not require fossil fuel combustion to generate heat. Heat pump or changeover systems are used for single zone applications or multi-zone applications that follow the same thermal profile. We typically install heat recovery VRF systems which use a branch circuit, or BC controller as we call it, that provides simultaneous heating and cooling in multi-zone applications with diverse thermal profiles. For example, hotels, office buildings, and any facility where some zones will require heating while others require cooling, all in the same building. One example of that might be, for example, a large glass structure office building. Let's say the sun comes up on one side of the building, those areas exposed to the sun might require cooling, whereas the other side of the building that's still in shade might require some heat in those areas. So let's break down those system types. At its most basic, a VRF system consists of an outdoor unit and a network of indoor units connected by refrigerant lines and governed by controls and sensors. VRF heat pumps are effective when all of a building's zones can be in the same mode at the same time, either heating or cooling. Now, the outdoor unit contains the compressor, condenser coil, reversing valve, and condenser fan. Each outdoor unit may be connected to multiple indoor units, and individual outdoor units may be combined to increase the tonnage. Each indoor unit contains a fan, filter, heat exchanger, and temperature sensors for the refrigerant and return air. Indoor units may be ducted, for example, horizontal ducted or air handlers, or ductless, like the examples you see here, the wall-mounted unit, the floor-standing unit, and the ceiling cassette. So in this example, you can see the outdoor unit on the left with refrigerant piping running to a variety of indoor units. And each outdoor unit has the ability to connect up to 50 indoor units, although I would say that's not the typical scenario, but it does have that capability. Each zone can have its own indoor unit that provides cooling and heating. Outdoor units capture heat from the outdoors that is transferred to indoor units during heating. Outdoor units reject heat transferred from the indoor units during cooling. When heat pumps or changeover systems, indoor units are either in all cooling mode or all heating mode. In this example that you see here, we're showing all the indoor units in the heating mode. Now let's talk about heat recovery systems. Heat recovery system, VRF systems, on the other hand, offer cooling and heating simultaneously within the same system. Now, as mentioned earlier, VRF systems with heat recovery are the ideal choice for office buildings, hotels, and any facility with diverse comfort needs that might require some zones to be heated while others are cooled. These systems use a branch circuit controller to direct refrigerant based on the conditioning needs of a particular zone, again, either heating or cooling. So how does this work? Well, one way to look at the BC controller is like a quarterback or a decision maker. By using a liquid gas separator, the BC controller separates the refrigerant so that some areas are cooled and some are heated. So each area or zone has its own indoor unit that provides the heating and cooling. So here again you see the outdoor unit on the left connected to refrigerant piping with the BC controller, which is that box just to the left of center, again connected to a variety of indoor units. But you can also see with the depiction of the blue and red lines that some areas are in heating mode and some are utilizing cooling. So instead of all indoor units being in one mode, a heat recovery system is capable of simultaneous heating and cooling. Now again, let's talk a little bit about how this works with the inverter-driven compressor. Each VRF outdoor unit has an inverter-driven compressor enabling the system to more successfully handle part load and low load conditions compared to conventional HVAC systems. The system only uses the precise amount of energy to meet the desired set point. The VRF system keeps occupants comfortable at the set temperature they choose, even as environmental conditions change. This efficient approach reduces monthly energy bills and increases occupant comfort. Heating and cooling loads continue to be important as passive house and other methodologies improve building envelopes and increase overall efficiency. This saves money and reduces energy consumption by up to 40% compared to conventional fixed capacity systems during shoulder seasons such as spring and fall. Conventional systems use a fixed speed compressor which cycles the unit on and off whenever the room dips below desired temperatures. Now that's depicted by the black dotted line that you see here. This type of system relies on an all or nothing philosophy with the compressor running at either 0 or 100%. This can lead to unpleasant temperature swings as the system strains to maintain a constant temperature. Now inverter compressors, on the other hand, are always running in the background, adjusting the compressor and modulating the speed in real time. That's represented by the green line here. By ramping up power to the compressor when needed, an inverter provides a more accurate, on-demand approach to temperature control. If your room's temperature is already a comfortable 72 degrees, for example, an inverter may slow the compressor's engine to a crawl. If your room is really warm, say 85 degrees, the inverter will push the compressor into high gear, reducing that temperature more quickly. Again, this is another source of energy savings as this eliminates the energy-intensive start-stop cycle of conventional HVAC systems. Now with our VRF systems, as you can see here, there are a variety of indoor unit options from ducted to ductless, or they can be used in combination. VRF equipment is very compact, saving space and offering a variety of aesthetic choices. Now here you can see the ceiling cassette, the ceiling concealed ducted unit, the wall-mounted unit, the air handler, and the floor-standing indoor unit as well. And as we like to say, we've got you covered from floor to ceiling. Let's talk a little bit about VRF controls and third-party systems. VRF controls software can integrate with non-proprietary platforms such as Tritium's Niagara 4 framework for advanced sequences and higher-level building automation systems control. VRF controls can integrate with third-party systems through standard protocols like BACnet or Modbus. This allows for centralized control and insight for facility managers. Let's talk a little bit about going beyond the mechanical bid. VRF installed cost has come down significantly in recent years. However, first costs can still be a hurdle. If you look exclusively at the mechanical bid, this makes sense. A developer or building owner seems to pay a premium to install VRF systems over perhaps VAV or other conventional type systems. But if you look beyond the mechanical bid and how the characteristics of HVAC systems affect the costs for other components of the building like plenums, ductwork, and structural steel, you can really start to see how even the first costs of VRF systems can be competitive with less energy-efficient alternatives. If we take an even more comprehensive view and look at life cycle costs for things like maintenance and energy bills, we start to see how the value of a VRF system can far exceed alternatives. If you've been following the news and developments around strategic electrification and decarbonization, you've likely come across information about carbon reduction initiatives across the country. Some of these are driven by state or city governments. In New York City, for example, Local Law 97 sets limits for the metric tons of CO2 a building over 25,000 square feet can produce per square foot. Building owners will be fined if their CO2 level emissions exceed the limits for their category. Fines in New York City, for example, will equal $268 per ton of CO2 above the allowed threshold. In other areas, state and city governments and even utilities might offer incentives for a building owner to install VRF systems. Massachusetts actually has been a leader in this area. I wanted to share this with you to talk a little bit about the growth of VRF technology. VRF was introduced in the United States over 15 years ago after many decades of prominence throughout the rest of the world. In fact, in Europe, it accounts for over 70% of the HVAC market. VRF systems are widely recognized by decarbonization advocates, policymakers, and interested members of the public as essential to decarbonization and moving to cleaner electricity for the built environment. We can see this in the studies and reports produced by organizations like the Northeast Energy Efficiency Partnerships, or NEEP, and the Vermont Energy Investment Corporation. Now, this chart is from NEEP's Variable Refrigerant Flow Market Strategies report and depicts how NEEP sees the adoption of VRF systems as a primary heating and cooling system for commercial and institutional buildings in the Northeast and Mid-Atlantic areas. The green line showing market penetration of over 40% by 2030 is the outcome NEEP and other electrification advocates are working toward. In any case, VRF adoption will continue to increase, and this creates opportunities for the HVAC contractors and engineers who have built experience and expertise with the VRF technology. Now that we've explored VRF technology, I'll turn the presentation over to Mike, who will go through more details about designing VRF solutions for cold weather applications. Mike?
Thanks, James. I'm going to talk about some specifics and drill down a little bit and talk about some strategies that you can employ in design to make sure that the VRF system can handle whatever cold climate you're applying it in. Just like any design of any HVAC system, the design objectives for the VRF design should look to meet objectives like reliable comfort, resiliency and redundancy, and energy efficiency. Traditional heat pump systems start derating rather quickly. A heat pump system from the 80s or the 1990s would start losing heating capacity around 40 degrees and drop pretty quickly from there. Generally, once you got to about 25 degrees, you would have to lock out the compressor or turn the system off and engage some sort of auxiliary heater. In most cases, in most climates, that's an electric strip heater and located in the ductwork. So when you need the heat the most with traditional heat pump systems, older style, you're getting the least amount, or you're getting the least efficient heat source available, i.e. the electric strip heat. The nice thing is with VRF, I'm going to demonstrate that we can design systems to work in all regions, even the coldest climates of our country. We're going to look at 6 different options for approaching and solving the derate challenge, because even though VRF systems or high-performance heat pumps don't derate nearly as quickly as traditional heat pumps, they do still derate. In other words, they lose heating capacity as it gets colder. So we need to make sure we have that planned in our design. So the 6 different design approaches we'll talk about. The first one is flash injection technology. The second one is auxiliary heat, or I'll just call it backup heat. That's really what it is, a full or partial backup heating system. The third one is sole source sizing of the VRF system based on the heating loads. The fourth one would be oversizing the heat in a DOAS system, or dedicated outside air system. The fifth one will be installing air-cooled outdoor units inside the conditioned envelope of the building. And the last one will be a little bit of talk about water source VRF design. So our first one, flash injection technology. Most of the VRF manufacturers have some version of flash injection technology. And the way it works is in the compressor that you see on the right, the scroll compressor, the cutaway, the refrigerant is traveling in the upward direction through the scroll compressor and into the dome of the compressor, where it's turned into a superheated gas, and then out the discharge pipe to the system for deployment and heating the space. With inverter-driven compressors, and really any compressor for that matter, as it gets colder outside, we need to drive the refrigerant temperature and pressure down, because the condenser coil in the heating mode is actually acting as the evaporator coil. Because really, the heat pump cycle is just the air conditioning cycle run in reverse. So to induce that heat to flow from the cold ambient air into the refrigerant across the coil of across the condenser coil heat exchanger, we need to drive that temperature and pressure lower and lower as it gets colder and colder. Well, there's limits to how much we can speed up the compressor. So as we speed up the compressor, it generates more friction. And if we didn't do anything else other than to just continue to speed up the compressor, eventually the friction would cause so much heat, it would cause the compressor to seize up. Analogous to a car engine, that if you run it without oil or you run it without coolant, it's going to seize up rather quickly. So what we do to counteract that with flash injection is meter or inject a small amount of flash gas or refrigerant into the dome of the compressor, which in the process of flashing actually removes that excess heat. We'll see that here on the diagram. So we have the compressor in the middle of the diagram coming out vertically, and the position of the reversing valve is such that that hot gas gets directed to the right to our indoor coil. And since we're in the heat pump mode, our indoor coil, which is normally our evaporator, is actually acting as our condenser. So it's rejecting heat to the air that's then sent to the space. The refrigerant comes out the bottom of that indoor coil, goes through what we call an LEV, linear expansion valve. After going through the linear expansion valve, it goes to a gas-liquid separator, which you can see at point D. The liquid comes off the bottom. The gas comes off the top because it's lighter. And then those two meet up again, except now through a heat interchanger circuit, they meet up again across a heat exchanger. So they're not actually in contact with each other at this point. So what was previously the liquid off the bottom of the separator is now going in the upward direction back to the compressor, metered through another linear expansion valve. And we just take that flash gas, or it's actually a mixed phase refrigerant, mostly gas, and meter it into the dome of the compressor. It evaporates as soon as it goes in. It removes that excess heat, and it keeps that compressor cool enough so that it won't seize up. Most manufacturers have a flash injection version of their product. You have to look at the specific capabilities of each manufacturer. Some manufacturers have up to 3 tiers, with the highest tier having the greatest heating performance, having basically a dedicated purpose-built cold climate unit. Some of those can operate at temperatures as low as 31 degrees Fahrenheit below zero. And the second tier, which gives a little bit less heat than the purpose-built unit, still is rated to minus 13 Fahrenheit. That's kind of the typical number you see with most manufacturers. And then the lowest heat output tier, it'll have different ratings depending on manufacturer. So usually in a cold climate, you're looking at either the purpose-built unit if you're in a real cold climate, like say Minneapolis, or maybe if you're someplace like Columbus where I live, where it gets cold, you might be able to get away with the mid-tier product in terms of the amount of heat that it puts out. The second option is auxiliary heat or backup heat. You can see the condensing unit or the outdoor unit in the lower right, and the indoor unit, wall-mounted in this case, next to it. And then to the left of that wall-mounted unit, you'll see an auxiliary heating, in this case, a baseboard steam radiator. It might be a turn-of-the-century Victorian house that has something like that. That auxiliary heat can be hydronic, it can be electric, it can be natural gas, it can be baseboard, it can be duct-mounted, it really can be just about anything. Typically, the VRF is the first stage of heat, and the auxiliary is the second stage or backup stage of heat. There are cases where you have district heat in a lot of large cities and in the real cold climates where they will look at a strategy of employing the district heat as the first stage and the VRF as the second stage. Either of those can be easily incorporated. Now we'll talk about a couple of methods for energizing that auxiliary or backup heat. One is based on an actual space temperature drop. I call that the space-by-space method. And then the second method would be based on outdoor temperatures. And I call that the global method. So we'll see some specifics in the next couple of screens here. With the auxiliary heat method, it's based on the actual space temperature. And the nice thing about this approach is you can do it basically zone by zone. You can put auxiliary heat in as many or as few zones as you want, and you can configure or set them up to operate uniquely. So for example, let's say you had a building, an older building, and you had a northeast corner of the building that had 2 exposures, that had lots of single pane glass, and it was the president of the company's office. Well, that might be a zone that you just want to make sure that you always have adequate heating capacity. So the way the space-by-space method or drop-in space temperature method works is we start at point 1 and we're going down in temperature to point 2. That's where our linear expansion valve, which is metering the refrigerant to that coil, is in the full open position. Well, we're not keeping up with the heating load, so we continue to drift down, and then we get to point 3, which in this case is 4 degrees below set point. Now that's adjustable. It can be generally adjusted between 2 degrees and 8 degrees below set point, but in this example, we've set it at 4. So at that point, our auxiliary heat comes on. So if it's an electric duct coil, that electric duct coil engages, temperature starts to rise back. Once we get to 0.4, that linear expansion valve starts modulating from open to closed, and then we get to eventually 0.5 as we catch up. The second method is the global method. So here we're changing over the entire system at one single time based on outdoor ambient temperature. So you can see here temperature's dropping as the arrow goes from right to left. And we have a couple of trigger points. In this case, we're triggering the system at point C, which is, in this example, 14 degrees Fahrenheit, and those can be adjustable. And then the second trigger point is point A at -4 degrees Fahrenheit. So before we get down to point C, or 14, our outdoor unit is operating as normal, and our 24-volt contact that pulls in our auxiliary heat is only operating typically related to being in the defrost mode. Then once we get below 14 degrees, the outdoor unit is operating, and the 24-volt contact is active, pulling in our auxiliary heat. Well, then we get to point A, where we put the outdoor unit in standby. Standby is just a fancy word for off. So at that point, we're running on just auxiliary heat. So there's a couple implications there. Number one is the auxiliary heat needs to be in every zone. You can't just put it in one or two zones like you could the previous method. The other consideration is that the backup heat has to be sized for the full heating load. Previously, with the space-by-space method, you really want to only size those coils for a smaller or incremental delta T, because you're running your heat pump heat, and then additive to that delta T that you get from your heat pump heat is the delta T that you get from the auxiliary heating coil. So you don't want to have a 20 to 25 degree delta T from your indoor unit heat pump coil, and then add another 25 on top of that and have a 50 degree delta T, and have, you know, air going out into the space that's going to cause cycling problems. So same thing, except in reverse as temperature's rising. The only difference here is that we stagger the trigger points. Instead of on the way temperature dropping, we're triggering at C and A. On the way up, we're triggering the reverse of that cycle at point B, which in this example is 8 degrees Fahrenheit, and point D, 20 degrees Fahrenheit. And we do that just so the system doesn't hunt. If the temperature, if you triggered on the way down and the way up in temperature at the same temperatures, you could, if you're hovering around that temperature, you could be slamming the system repeatedly into and out of auxiliary heat. So staggering those temperatures helps prevent that phenomenon. So what criteria might you use to choose which of those two methods? Well, we talked about the fact that you can do the space by space in just a few zones. You can do it in all the zones. You really have a lot of flexibility. Whereas the global method, you need to do it on the entire building or the entire system. The other one is that top line there, space temperature. So with the method one, space by space, the temperature by definition has to drop below set point. So if you're triggering at 4 degrees below set point, and your set point is 72, that means your auxiliary heat's not kicking in until it gets to 68 degrees, and that might be objectionable for some people. That they probably will notice that 4-degree temperature drop. Whereas with the global method, you're turning this auxiliary heating system on regardless of what indoor space temperature is doing. You've really decoupled those two. Another one that's not on this list is really first costs. Where we usually see the global system employed is where there's some existing infrastructure, heating infrastructure that's already there in an existing building. Maybe it has pumps and boilers and piping that's relatively new, 5 or 10 years old. It's in good shape. Why not spend a little bit extra money to put that in as an auxiliary heating system? Really, your only incremental cost is the controls related to doing that. Whereas if you're building a new building, we see very few people doing that full backup heating system, that global method, just because of first cost. So that might be a consideration. The other one, morning warm-up, method one, space by space, the morning warm-up is usually going to engage if you're setting the building back very much in temperature. Now with VRF systems, you don't want to be too aggressive in night setback. You might typically only want to go about 5 degrees, 4 to 5 degrees, maybe not 8 to 10 degrees. But if you're at 5 degrees below set point and you go back to your normal occupied settings, you're going to engage that auxiliary heat system. Whereas with the global method, once again, it's decoupled. It's operating based on ambient temperature, not based on space temperature. So how often will the auxiliary heat run? If you're using, what we've seen is sometimes people will go to the expense of putting in a full system, full backup or auxiliary system, and it really doesn't run at all, which is just a big waste of money. So if you have a flash injection or that dedicated cold weather purpose-built unit, it may not run at all, or it may run very little. So it really depends on the specifics of the application and the specifics of the climate. But most of your winter days are relatively mild. ASHRAE has the typical design temperature in the winter is the 99.6 design temperature. So for Columbus, that's 0. Well, that means that 0.4% of the time it's colder than 0, and 99.6% of the time it's warmer than 0. Although today it doesn't feel much warmer than that. So along those lines, if we look at a map of the U.S., this is interesting. This is how many bin hours are in the band between 50 and 80 degrees Fahrenheit. So you can see for Chicago, it's over 4,000 hours. So there's only 8,760 hours in a year. So almost half the year you're in that bucket. And then the other half of the year, you're either colder than 50 or warmer than 80. You look at San Diego and it's 8,400 hours. Almost every hour of the year is between 50 and 80 degrees. So the nice thing is VRF systems, even though we're sizing them for the extremes, so we're sizing them in the case of where I live in Columbus for that 0-degree day in the winter and that 95-degree day in the summer. The nice thing is they unload very effectively at part load and very efficiently. You get nice smooth operation at all those part load hours. Third option is what we call sole source sizing based on heating. And I want to emphasize here those words based on heating. When we first brought the product to the United States, most designers laying out systems were used to sizing things off the cooling load and just oftentimes assuming that the heating load was enough. For example, if you have a 25-ton gas electric rooftop unit, I bet if you check most manufacturers, there's going to be two choices. You can get a low heat unit or a high heat unit. If you're in the colder climates, you're using the high heat unit. If you're in the more temperate climates, you're using the low heat unit. Well, with VRF, what we find is that the nominal tonnage is often not determined by the cooling load, but rather by the heating load. So the heating load can actually bump you up 1 or 2 sizes maybe from what the cooling load would have caused the size to be. So we don't see that as much anymore because each generation of VRF that gets released has more heating capacity. It's generally a more efficient and a little bit smaller footprint too, which is kind of nice. So we're seeing less of that, but you just got to be careful that when you size the units, you're looking at your block or peak heating loads as well as your cooling loads. Also, that last line there, make sure you're looking at your indoor unit supply air temperature on a design winter day. When I'm designing systems, I like to ideally, where we live here in Ohio, see a supply air temperature maybe around 90 degrees or higher on that worst case winter day. If you're in Atlanta, maybe you can get by with a little bit less discharge air temperature. With traditional heat pumps, the discharge air would often go down into the mid to upper 70s, and people would complain of cold air blowing on them. They could feel drafts, and that's why heat pumps kind of got a bad name. Well, these high-performance heat pumps, you can see 90, 100, 110 degree air is not uncommon. So you just want to make sure you're looking at that and making sure that you as a designer are comfortable with whatever that temperature is. So here's just a little example of sizing based on heating or sole source sizing of the VRF system. So we have a university building. It has a winter design temperature of 5 degrees. So maybe this is Louisville, Kentucky, someplace like that. Our heating load for that space part of the building is 120 MBH. So which nominal model size would best satisfy the heating load above 120 MBH. So our first option is outdoor unit 1, which gives us nominally 188 MBH. And nominal just means at standard rating conditions, which happen to be 47 degrees Fahrenheit for heat pumps. Or the second option, outdoor unit 2, which is a nominal 160, and the third unit, a nominal 135. Now, bear in mind, when you see a model number and you see 120, that's related to the nominal cooling capacity, not the nominal heating capacity. But you can usually use a rule of thumb of about 1.25 for your heat of compression. So if you take that 120, the model that's got a 120 in the model number, take that times 1.25, that'll be generally your nominal heating output because of the heat of compression ratio. So in this case, we actually look at the curves, and you can see that they slope from right to left and slope down as it gets colder out. And in this case, we want to look at 5 degrees, which is circled in red. So we go up and where it intersects with the black curve, and then we go over to the left, the vertical axis, and we see our D rate there is a 0.65. So we're taking that 188 MBH, which was that first outdoor unit choice, times 0.65 means it nets us 122 at 5 degrees. 122 is greater than 120, so we have our unit selection size, our nominal unit selection size for purposes of heating. We also generally want to make sure we don't forget about the indoor units, as they often or almost always have to be upsized too, if you want to be able to really absorb that additional heating capacity that a larger outdoor unit is going to give you. And it just has to do with matching the heat transfer of the aggregate of the indoor unit coils to the capacity of the outdoor unit coil. An analogy that I usually like to give is if you have a furnace with an A coil in your house, and let's say it's a furnace that has a 2-ton drive, and you've got a 2-ton A coil, and you've got a 2-ton condensing unit. You do a sunroom addition, and you've got another 1/2 ton. Well, if you go and put a 2.5-ton condensing unit, but you don't go and change out your A coil, and you don't adjust the blower to get more CFM, you're really not going to get that 2.5 tons out of the condensing unit. So this is the same thing, except we're talking about the heating cycle instead of the example I gave, which was the cooling cycle. So option 4 is oversizing the heat in the dedicated outside air systems. So almost all of our DOAS units nowadays in colder climates have heat recovery energy wheels. Most of them are natural gas furnaces in them. And we generally size those to deliver room neutral air. So in the summer, we're cooling it down to maybe 50 degrees Fahrenheit and then reheating it to around 70. So room neutral air is generally considered air that's supplied to the space at between 70 and 75 degrees and in a dehumidified state. And then in the winter, we may or may not have that heat exchanger sized for a delta T that's very large. If we have an energy wheel, we're generally going to come off that wheel at around, say, maybe 45 or 50 degrees Fahrenheit on a design winter day. So maybe we have another 40-degree delta T from our gas heat exchanger where we can deliver that air to the space either at a room neutral condition or even at an above room neutral condition because we can use that heat. Well, instead of putting in a smaller gas heat exchanger, why not just up the size of that gas heat exchanger? So instead of putting in maybe a 400 MBH heat exchanger, put in a 600 MBH heat exchanger. Your incremental cost is virtually nothing. And then if you also add a recirculation air damper, because most standard DOAS units don't come with a recirculation air damper because they're meant to deliver only outside air, then you can use that recirculation air damper in either a morning warm-up or daytime warm-up or even an emergency situation where, say a compressor's out and it's going to take 12 to 24 hours to get that compressor replaced and get that system up and running. So you could put that unit in recirc, close that outside air damper just on a temporary basis, and run that gas heat exchanger all the way up to where you're delivering 110, 115, 120 degree air to the space. So option 5 is installing air-cooled outdoor units inside the building or inside the conditioned envelope. You can see here the picture, we've got the access door open. And you can see the outdoor unit has actually got ductwork coming off the top, which turns to the right and discharges and goes out the building. But if you look to the bottom side of that, you'll see another little baseboard radiator. So my guess is, I don't know where this installation is, but that was probably existing infrastructure that was either repurposed in the building and now is being used as a mechanical room to put those outdoor units inside. You know, the really nice thing is you can keep the equipment out of the elements, so it'll last a lot longer. It's not getting rained on and snowed on and hailed on, and animals can't get into the control cabinet and eat the wiring. All kinds of considerations like that. If a service tech has to go work on it, he can do it in a conditioned space. So just a lot of benefits to that. So that might be a case also where you don't have space on top of the building. Maybe there's already a bunch of rooftop equipment, and if you're in a dense urban environment, maybe there's no space outside at ground level of that building either. So that opens up some options. We don't see this employed that much because if you're doing it from start to finish, schematically, that looks like what you see here. So it gets fairly expensive. So most people aren't willing to pay that first cost. Once again, unless some of that infrastructure is already there. So in this case, we show a gas unit heater in that mechanical room. You can see that condensing unit is ducted, and that ductwork comes up and bends to the left, and then it can either go out the exhaust air louver, or it can be recirculated back into the mechanical room. And you'll see on the right, there's a fresh air louver. So essentially what we do is at more modest winter temperatures, we're just using that as a single pass plenum. So the air is coming in that outside louver. It's actually going across the condenser coil where the VRF system can operate just like it normally would, out the condenser fan, which we can set for a higher static pressure capability, and then out that exhaust air louver. So that's at the more mild temperatures. Once it gets colder, we actually close the exhaust air louver and we open up that recirc damper, and we essentially turn that into a recirculation air plenum, and then the unit heater comes on, so we heat the space, which is comprised of air being recirculated, which is going across the condenser coil, and so the VRF system is absorbing the heat from the unit heater, not directly, but indirectly. The unit heater is heating the air, and then the air is passing across the condenser coil. So that gas unit heater heat is making its way into the VRF system, and then the VRF system is just layering the heat of compression on top of that heat. The last option is water source VRF systems, and once again, equipment's all indoors, so you get the advantages of the equipment lasting longer but being in a controlled environment. We really don't have to worry as much about derate because outdoor air, even though it's getting cold, our loop temperature, which we'll see on the next screen, we can maintain at a controlled temperature. Now, our capacity, both in the cooling and the heating mode, is a function of entering water temperature. And lastly, we can get these systems, just like the air source systems, you can get them in heat pump changeover systems, or you can get them in heat recovery systems. So here's just a real simple schematic of a water source VRF system. We've got the loop is in green there, the water loop, and the VRF condensing unit's either pulling heat out of that loop if it needs to heat the space, or it's dumping heat into that loop if it needs to reject heat because it's in the cooling mode. And then the loop gets generally controlled just like you see in a standard water source heat pump system between about 60 and 90 degrees. So at 60 degrees, we turn the boiler on. When it gets below that, if it gets above 90, we turn the cooling tower, which is got to have a heat exchanger because we don't want to send dirty cooling tower water through the condensing unit. They have what are called brazed plate heat exchangers, so you got to worry about fouling and keeping them relatively clean. Installation considerations, I'll go through these rather quickly. You want to get heat pumps up off the ground, put them on a stand. There are manufacturers that make pre-made stands, or the contractor can make them. You want to make sure they're open so snow can go through them and not drift up against the unit. And this is so that you don't have coil damage from defrost water refreezing as it sheds down the unit. Also, high wind conditions, you want to make sure that you have 4-point restraints. So if it's on top of the building, it's going to catch the prevailing wind. That can cause a lot of force on the unit. The low ambient hoods and the snow and hail guards can act as a scoop to the wind, so there can be a lot of lateral force on those units. If it's protected by the building, that's usually a different story, and you don't need this sort of arrangement. And then you got snow and hail guards for obvious purposes. The snow hoods are good if you're under the drip edge of the roof and you're worried about icicles. So an icicle coming down in the spring as it's melting can go right through. We've seen them come right through the condenser fan shroud and destroy the condenser fan blades and do expensive damage. If you have the snow hood, you're just talking about a piece of sheet metal that would need to be either replaced or maybe some dents hammered out. So snow and hail guards, depending on the specifics of the installation. So just generally speaking, planning for winter, you can see some residential units there. They're up on those pre-made manufacturer supplied stands, super stands, you heard them called. So get them up above the snow line. Think about ice accumulation. So you don't want defrost water refreezing on sidewalks. So think about slope and grade and things like that. Use where you need panel heaters or base pan heaters. There's accessories in units, like in our purpose-built cold climate units. Generally, there's some sort of base pan heater or panel heater built in that product as standard. That's why it's called purpose-built for cold climate. James is going to talk about some third-party studies, and I'm going to turn it over to him. If you have any questions on the AC Marriott project he's going to talk about, I sold that project, so I'm intimately familiar with it. So James, it's all yours.
All right. Thanks very much, Mike. Yeah, well, I was going to reference that project. I thought that was one that you'd worked on. So, I wanted to share with everybody now that we have a good understanding of VRF technology, and as Mike has shared and looked into opportunities for cold climate applications, we did just want to share a couple of real-world examples on how VRF systems resulted in energy efficiency for buildings. The first case study is Minnesota Power. And this is located in Colquitt, Minnesota, which is in upper Minnesota, a couple hours north of Minneapolis and just west of Lake Superior, so obviously a very, very cold area. Their company headquarters is a 5,000 square foot office building. The company prides itself on helping the state reduce reliance on oil and natural gas. They're able to retrofit the building and replace a faulty HVAC system with the desire to promote strategic electrification and demonstrate the efficiency of VRF systems. Now, as I mentioned, this is a very cold climate area with a low ambient design temperature of minus 20 degrees Fahrenheit. Now, based on the 30-year averages, design temperatures only occur during 1% of all hours in a year. This challenge was solved with a heat recovery system equipped with hyperheating technology and auxiliary heat. Minnesota Power is now an example of a highly efficient, sustainable heating and cooling facility in the state. Minnesota Power has a conference room where they've installed 2 individual thermostats side by side to demonstrate how heat recovery works. Each thermostat is connected to a separate indoor unit and lights up either blue or red for cooling or heating. Now, as Mike mentioned, this is the AC Marriott Bridge Hotel, built in 2007 and located in Dublin, Ohio. And this is a 140,000 square foot, 8-story building. Now, Dublin, if you're not familiar with it, is an affluent suburb of Columbus and home to several Fortune 500 companies and hosts the renowned Jack Nicklaus Memorial Golf Tournament. We're starting to see a shift toward VRF within the hospitality market. Now, the big reasons for this are energy efficiency through heat recovery, maintenance, comfort, and the acoustics. When guests stay at a hotel and hear a conventional system kick on, it may annoy them or even wake them up in the middle of the night. Quieter VRF systems provide a much better experience for guests in terms of acoustics. VRF systems provide much better comfort in terms of temperature and humidity control. Again, unlike conventional systems that constantly turn off and on, a VRF system runs continuously and efficiently while also adjusting fan speeds to continuously remove moisture. Now, Mr. Orkun Türkay, general manager of this hotel, told us, quote, the most important thing for our hotel guests is that HVAC operation is simple, comfortable, and unnoticed. The hotel was originally designed around a water source heat pump system based on its efficiency and individual room control. The developer brought Mitsubishi Electric Trane into the project to look at the variable refrigerant flow water source systems just before the bid was about to go out. The developer liked the technology, especially the equipment and installation savings of over $500,000, as you can see here on the screen, versus the originally specified water source heat pump systems. The advantages of water source VRF system in extremely cold climates include the fact that with water as the heat sink, all the VRF system's equipment can be installed indoors. Indoor installation means the equipment is better protected from outdoor conditions and can deliver optimal performance with even lower degradations of performance in extreme cold. So with harsh winters and temperatures that dip well below freezing, water source VRF helped improve the guest experience for the AC Marriott. I did just want to share one product that we have coming out in the near future, and that is a new heat pump water heater. This water heater is designed to produce high volume hot water for commercial and industrial applications. Now, some typical applications would be for multifamily, for example, or hotels, gyms, senior living facilities perhaps, anywhere that calls for hot water when your guests or tenants need it on demand. You can see from the diagram we have the heat pump water heater on the left, which connects to a holding tank and piping to deliver the water. These units can be combined together with multiple tanks to deliver large volumes of hot water. And because of some of the patented technology, we anticipate this product to have a high coefficient of performance, making it much more efficient than traditional water heating options. Also, this product utilizes CO2, an environmentally friendly natural refrigerant, which doesn't destroy the ozone layer and has significantly low global warming potential. By using CO2, this unit can contribute to the reduction of harmful emissions. Some of the other features include providing high temperature hot water up to 176 degrees, along with the ability to operate at low outdoor temperatures as low as -13 degrees. So again, this heat pump water heater is something we're looking to be launching next year. Now, some of the takeaways from today's presentation: modern VRF systems offer cold climate capabilities far beyond older systems. With flash injection technology that Mike talked about and today's compressors, VRF systems perform reliably in climate zones 1 through 6. Some systems, as Mike also talked about, provide heat down to -31 degrees. We talked about some of the challenges of cold weather climates and the use of flash injection technology, auxiliary heating options, DOAS systems, indoor installation, and water source VRF systems, as we did with the Marriott example. We talked about preparation for cold weather, which includes installing outdoor units above the snow line, using snow hoods, as well as following best practices and staying current on how manufacturers are moving VRF technology forward. And finally, VRF systems are positioned for growth and wider adoption as decarbonization and strategic electrification gains momentum. This cold climate performance of VRF systems makes these initiatives feasible and solves challenges for building owners. This concludes the prepared portion of today's webinar. Mike and I enjoyed discussing VRF technology and the opportunities for applying VRF technology in cold climates. We hope you found the information to be valuable, and we look forward to answering your questions in just a few minutes. I know we're getting a little bit short on time. But if you'd like to submit a question, please do so through the Q&A interface. I did just want to share, highlight a few resources among many others available for your use after this presentation concludes. These resources include our website, metahvac.com. You'll also see a link to our quarterly engineer, architect, and facility manager newsletters. In addition, we've included a link to our case study library where you can explore how VRF is applied in a variety of applications with over 170 different options on the website, with case studies involving hotels, office buildings, education facilities, and many more. And lastly, a link to locate a qualified HVAC contractor or VRF distributor. So on behalf of Mike, thank you again for your time and attention today. And with that, I'll turn the presentation over to Andy, who will begin our Q&A. Andy?
Thank you, James. All right, no time for quips. Let's get right to it. So, first question. Do VRF systems offer an easy way to integrate with fault detection and diagnostic systems and provide immediate and visual knowledge about problems that may develop?
Yeah, I'm not sure if that question is relating to like the maintenance tool that we have that's able to plug into the outdoor units and provide that type of diagnostic data. I'm not sure if you have any information on that, Mike.
It was a pretty general question that requires a specific answer, so it really would be hard to answer without knowing more of the specifics of what the questioner was asking.
Okay. So next question. Seems like more of a statement and looking for validations. So you do the pickup heating with the DOAS system, right? When the outdoor air temperature is low and the heat is injected by the DOAS to neutral temperature, the heat pump has only sensible cooling and heating requirements. Is that correct?
If you bring the air in, I'm sorry, I just was going to jump to the answer. If you bring the air in at a low enough dew point, the answer would be yes. There's a lot of talk right now about the standard 55-degree dew point that most designers use, adding latent load to the space on high humidity days. So there's a lot of talk about lowering that to a lower temperature between, say, 45 and 50 dew point, in which case, yes, at that point you pretty much decouple the sensible and the latent load, and the DOAS system is handling almost all or all of the latent load, and the VRF system is left handling mostly or all sensible load. So you kind of get each system doing what it's best at.
All right. Next one. How does the defrost cycle affect the heating capacity?
It reduces it, and there's a derate factor in the manufacturer's software programs that accounts for that. It's usually on the order of about 5% of the time, but it only happens at certain conditions. So defrost is actually pretty common when the temperature's in the 20s outside because the air contains a lot of moisture. Once you start getting down into the low teens and single digits and colder, the outdoor air really doesn't and can't have much moisture in it, so you don't see near as much defrost. So you have kind of that intermediate temperature in the 20s where you tend to see more defrost, but that's accounted for in the selection software programs that are out in the market for all the manufacturers.
Okay. For moderately cold climates, let's say negative 18 degrees Celsius, if we use hyperheat flash injection technology in order to avoid using backup heat, would it be sensible to purposefully oversize the outdoor units?
So 18 degrees Celsius, I'm trying to do the math in my head to what that is in Fahrenheit. I personally think the flash injection is probably overkill at what that temperature correlates to in Fahrenheit. So generally we're seeing the dedicated purpose-built cold climate flash injection technology used in the really, really cold climates. And then in the just plain cold climates, we're seeing the next tier down, what in our case we call the high efficiency product, because it still gives a pretty good heating output because it really has flash injection light. And then in the real temperate winter climates, mostly below the Mason-Dixon line, we're seeing the standard efficiency product, unless the owner wants to bump up to the high efficiency product because of efficiency reasons, nothing to do with cold climate design.
Okay. There are a number of questions with regard to indoor installation. So try to run through a few of them really quickly. Are there kits that Mitsubishi Electric or other manufacturers supply for facilitating indoor installation?
Are there kits? I guess I'm not sure what type of kits are being talked about. There are kits for installing what we call cassette-mounted units into ceiling grids and ceiling tiles. So there are those kinds of kits. I'm not sure if that's what the questioner is referring to. So I believe the answer is yes. There's also what's called LEV kits, where we can take our condensing units, our variable speed condensing units, and match them up with third-party DX coils. So that opens up a world of opportunities of matching with air handling units and all kinds of equipment with the third-party DX coil being able to match to our condensing unit with the LEV kit. So there's two examples I can think of.
Okay. Next one. Regarding the installation of outdoor units inside the building, what is the potential effect on efficiency during cooling, if any?
It would be minimal, because on that 90-degree day, the mechanical room really is going to be almost identical to what the outdoor temperature is in both temperature and humidity. So it would be, you got a little bit of losses from the static pressure of the ductwork attached to the top of the unit and the dampers. So you might have 0.2 inches of static. So you're going to lose a little bit of efficiency as the fan has to overcome that static, but I would say that's pretty minimal.
Okay. There are a few questions inquiring whether there are VRF-like systems for residential applications, like single-family residential homes. Do you want to comment on that?
Yeah, absolutely. We have a whole lineup, as do other manufacturers, of equipment that is built for the residential market. We don't typically call it VRF because that implies a commercial product, generally three-phase product, 6 tons and above. So you won't hear it called VRF, but it does move variable amounts of refrigerant, and it does have an inverter-driven compressor. So technically, those are VRF systems, although the market generally doesn't refer to them as that. So the answer to the question is yes.
Yeah, and I'll just add, there's also like single zone applications for homes as well as multi-zones. And if you see on the screen there, the website, metahvac.com, there's also, if you go there, there's a link to our residential website.
All right, I'm going to steal a little bit more time. There are some questions with regard to derating at higher altitude. So what is, we know the derating at cold temperatures for outdoor units and indoor units at, say, 6,000 feet.
Yes, we compensate for that. The software is able to compensate for altitude with the right inputs. I generally don't work in high altitude conditions, so I don't do it on a day-to-day basis. But yes, that can be compensated for easily.
Okay. Is there a rule of thumb for the cost increase percentage if we go from a system that can operate at negative 13 degrees Fahrenheit to a system that can operate at negative 31 degrees?
Yeah, the outdoor units are more expensive, but when you average that cost across all of the equipment, including the indoor units and VC controllers and controls, and then you also average it across the mechanical installation, I would say out the door total cost, you were talking maybe a couple of percent. I would say maybe 2 or 3% if I had to put a guess to it.
Okay. This may be the last question. I'm waiting for them to pull the plug. Can you comment on how to meet ASHRAE standards 15 and 34 for safety?
Yeah, we get that question a lot, not as much nowadays. So with ASHRAE 15, you have to look at the possibility that all of the charge could leak into the smallest enclosed space, and make sure that resulting concentration is below 26 pounds per cubic foot. So if you're doing a design and you've got it, roughed out, and you find that you've got too much refrigerant in the system for the smallest size space, there's a number of different things you can do. You can split it into smaller systems. You can take that space and put it on its own dedicated mini split, which is exempted. You don't even have to worry about the refrigerant charge. You can put in transfer grills to create connectivity of spaces. So there's a lot of different things you can do to design around that. With hotels, what I've found is that generally about 10 tons, you need to stay with 10-ton and smaller systems, because once you start getting bigger than that, you'll start running into the refrigerant concentration or RCL limits that are imposed by ASHRAE 15. So you generally see smaller condensing units or outdoor units in hotels because of that, because you can't put a big door undercut in a hotel for privacy reasons.
Okay, I think that's all we have time for. So, James, I'll pass it to you if you have any concluding words.
All right, thanks, Andy. Thanks, Mike. I apologize, everyone, for running a few minutes over. For any questions we weren't able to get to, we'll be reaching back out. But we do appreciate everyone's time today, and we hope you found the information to be useful. And on behalf of ASHRAE Journal, thank you again for joining us today, and have a great day. Thank you.